On May 12, 2022, at 9:07 in the morning Eastern Time, scientists held simultaneous press conferences in cities around the world: Washington, D.C., Tokyo, Santiago, Munich, Taipei. In each location, astronomers unveiled the same image, a glowing ring of orange and yellow light, smeared and asymmetric, surrounding a dark void. The image was blurry by everyday standards. You wouldn't hang it on your wall. But it represented something unprecedented. Humanity's first direct view of the boundary between our universe and something beyond. It was a photograph of the monster lurking at the center of our galaxy. For generations, astronomers suspected something massive resided there. They watched stars whip around an invisible point at millions of kilometers per hour. They measured radio emissions from something extraordinarily compact. They built theoretical models and ran computer simulations, but they had never actually seen it. And the reason we had never seen it is simple. What sits at the heart of the Milky Way is, by definition, invisible. It's a black hole, and not just any black hole, a supermassive one, 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. It's called Sagittarius A, pronounced Sagittarius A star, and it's been there for billions of years, quietly anchoring the rotation of hundreds of billions of stars, including our own Sun, which orbits around it once every 230 million years. What you're about to learn is the story of how we found it, how we photographed the impossible, and what this discovery tells us about the nature of space, time, gravity, and our place in the cosmos. This is not speculation. This is physics, and it changes everything you think you know about what holds the universe together. In the pages that follow, you'll learn about Einstein's revolutionary theory of gravity, about the mathematical proof that black holes must exist, about the decades of observations that narrowed in on the galactic center, and about the extraordinary technology that finally photographed it. You'll learn what happens when matter falls into a black hole, how black holes evaporate over eons, and what puzzles remain unsolved. To understand what's at the center of our galaxy, we need to start with what a black hole actually is. And to understand that, we need to go back to 1915, to the year that changed everything we thought we knew about space, time, and gravity. In that year, Albert Einstein published his general theory of relativity. It was a radical reimagining of gravity. For over 2 centuries, Isaac Newton's laws had reigned supreme. In Newton's universe, gravity was a force, an invisible attraction between objects with mass. The Earth pulls on an apple, the Sun pulls on the Earth. And that's that. Einstein said something different. He said gravity isn't a force at all. It's geometry. Mass and energy bend the fabric of space and time itself. When an object moves through curved space-time, it follows the path that curved geometry dictates. What we perceive as gravitational attraction is really just objects following the contours of a universe warped by mass. Think of it this way. Imagine placing a bowling ball on a stretched rubber sheet. The bowling ball creates a depression, and if you roll a marble nearby, it curves toward the bowling ball. Not because the bowling ball is pulling on it, but because the marble is following the curved surface. That's what gravity actually is. But the analogy only goes so far. In the real universe, the rubber sheet is 4-dimensional space-time, and the curvature affects not just space, but time itself. Near a massive object, clocks run slower, light bends, the geometry of existence itself warps. And when you have enough mass concentrated in a small enough space, the curvature becomes so extreme that not even light can escape. That region of space becomes a one-way door. Anything that enters cannot leave. We call that door the event horizon, and the object it surrounds is a black hole. The name black hole wasn't coined until the 1960s. Physicist John Wheeler is usually credited with popularizing it, though he may not have invented it. Before that, these theoretical objects went by less evocative names: frozen stars, collapsed stars, gravitationally collapsed objects. But black hole captured the public imagination, and the scientific community soon adopted it. The name is perfect: a hole in space, utterly dark, from which nothing returns. Now, here's the thing about black holes that Einstein didn't like. They were a consequence of his own theory. Just weeks after Einstein published General Relativity, a German physicist named Karl Jansky was serving on the Russian front during World War I. While sheltering from artillery fire, Schwarzschild solved Einstein's field equations for a simplified case: a perfectly spherical, non-rotating mass. His solution described a point of infinite density surrounded by a spherical boundary from which nothing could escape. Einstein found this disturbing. He didn't believe such objects could actually exist. They were mathematical curiosities, artifacts of simplified equations, not things that would form in the real universe. In a 1939 paper, Einstein tried to argue that black holes couldn't form through natural processes, that some mechanism would always intervene to prevent matter from collapsing completely. Einstein was wrong. The universe doesn't care what physicists find disturbing. The equations describe reality, and reality includes objects so massive and so compact that not even light can escape them. For decades after Schwarzschild's solution, physicists debated whether black holes were real. Many assumed they were mathematical pathologies, singular solutions that appeared in idealized calculations but would never form in the messy reality of the cosmos. Surely, they thought, real collapsing stars would find some way to avoid becoming black holes. Some asymmetry, some rotation, some pressure would halt the collapse. In January 1965, half a century after General Relativity was published, and a decade after Einstein's death, the British physicist Roger Penrose proved that black holes aren't just possible, they're inevitable. If enough matter collapses under its own gravity, a black hole must form. This isn't a maybe, it's a mathematical certainty, as sure as 2 + 2 = 4. Penrose introduced the concept of a trapped surface, a closed two-dimensional region where all paths, including the paths of light itself, lead inexorably inward toward a singularity. Once such a surface forms, the creation of a singularity cannot be avoided. This work was so foundational that Penrose received the Nobel Prize in Physics in 2020, 55 years after the original paper. The Nobel Committee cited him for the discovery that black hole formation is a robust prediction of the general theory of relativity. So black holes are real. They form when massive stars die, when stellar cores collapse. They exist throughout the universe, invisible graveyards of dead suns. Astronomers have detected dozens of stellar mass black holes in our galaxy through their gravitational effects on companion stars and through the gravitational waves released when they collide. But the black hole at the center of our galaxy is different. It's not the corpse of a single star. It's something far more massive, far more mysterious, and far more important to the structure of the cosmos itself. first hint that something strange lurked at the heart of the Milky Way came in 1933, and it came by accident. Karl Jansky was a 27-year-old radio engineer working for Bell Telephone Laboratories in New Jersey. His job was utterly mundane. Find out what was causing static on transatlantic phone calls. Bell Labs wanted cleaner connections, and Jansky was tasked with identifying sources of radio interference. He built a rotating antenna, a contraption of wooden beams and metal tubes mounted on wheels from a Ford Model T, allowing it to spin in a full circle every 20 minutes. He called it his merry-go-round. From his post at a Bell Labs facility in Holmdel, New Jersey, surrounded by potato fields, Jansky spent months cataloging sources of interference. With this device, he tracked down interference from nearby thunderstorms, distant thunderstorms, and something else. There was a faint hiss, a steady, persistent signal that didn't correlate with storms. It peaked at the same time each day, almost. Not every 24 hours, but every 23 hours and 56 minutes. Jansky puzzled over this for months until a colleague, astrophysicist Albert Melvin Skellett, pointed out that 23 hours and 56 minutes is the length of a sidereal day, the time it takes for Earth to complete one rotation relative to the fixed stars rather than relative to the Sun. The signal wasn't coming from Earth. It wasn't coming from the Sun. It was coming from space. Jansky was puzzled. He was a radio engineer, not an astronomer, but he was methodical and he was curious. He spent months comparing his observations with star charts, learning enough astronomy to make sense of what he was detecting. By comparing his observations with star charts, Jansky traced the signal to the constellation Sagittarius, the direction of the galactic center. On May 5th, 1933, the New York Times ran a front-page story. New radio waves traced to center of the Milky Way. NBC broadcast a live demonstration of Jansky's star noise to a national radio audience. Static hissing through speakers, an alien sound that listeners were told originated from the heart of our galaxy. Jansky had accidentally discovered radio astronomy. He had detected something screaming in radio waves from the center of our galaxy, and nobody knew what it was. The irony is that Jansky couldn't continue his research. Bell Labs had no interest in astronomical radio waves. Their business was telephones. They reassigned Jansky to other projects. He wanted to build a large dish antenna to study the galactic signal in more detail, but the company refused. Jansky died in 1950 at age 44, never knowing what his discovery would ultimately reveal, but others picked up where he left off. An amateur radio enthusiast named Grote Reber built a parabolic dish antenna in his backyard in Illinois, the world's first true radio telescope, and spent years mapping the radio sky. After World War II, technologies developed for radar were repurposed for astronomy. Radio telescopes sprouted across the globe, in England, in Australia, in the Netherlands, in the United States. Each one peered at the universe in ways that optical telescopes couldn't. For decades, astronomers studied this radio source, eventually naming it Sagittarius A. But they couldn't see what was causing it. Visible light from the galactic center is blocked by vast clouds of dust and gas, 25 magnitudes of extinction, meaning the light is dimmed by a factor of 10 billion before it reaches Earth. To understand how extreme this is, if you tried to see the galactic center with your eyes, or with an optical telescope, you'd see nothing but dark dust clouds. It's like trying to see through a brick wall. The center of our own galaxy was invisible to us for most of human history. But radio waves and infrared light penetrate the dust. And in the decades following Jansky's discovery, radio astronomers mapped the galactic center in increasing detail. In the 1970s, they identified a compact, intense radio source at the very center, smaller and brighter than anything around it. They called it Sagittarius A, with the asterisk indicating something special, something distinct from the broader Sagittarius A region. Observations in the 1980s showed that Sagittarius A was extraordinarily compact, no larger than our solar system, despite being the brightest radio source in the galactic center. This was a puzzle. What could pack that much radio-emitting energy into such a small space? Some astronomers speculated it might be a cluster of neutron stars or stellar black holes. Others proposed exotic explanations, but the evidence kept pointing in one direction: a single, extremely massive, extremely compact object, a supermassive black hole. The question was, how to prove it? To see the center of the galaxy, you need to look in wavelengths that penetrate the dust, infrared and radio. And when astronomers finally did, they found something extraordinary. In the early 1990s, 2 independent research teams began an ambitious project. They would track the motions of stars near the galactic center using the largest telescopes on Earth over the course of years and decades. The goal: determine whether the radio source Sagittarius A arm was actually a supermassive black hole. One team was led by Reinhard Genzel, a German astrophysicist at the Max Planck Institute for Extraterrestrial Physics. The other was led by Andrea Ghez, an American astronomer at UCLA. They were rivals, competitors, working in parallel on opposite sides of the planet. Both teams faced the same challenge. The galactic center is 26,000 light-years away. At that distance, the individual stars near the center appear impossibly close together, like trying to distinguish individual headlights in a city 1,000 miles away. And Earth's atmosphere blurs everything, making precision measurement nearly impossible. The atmosphere is a turbulent ocean of air, constantly mixing warm and cold layers, bending and distorting light as it passes through. This is why stars twinkle. The light from a point source is scattered by atmospheric turbulence. For casual stargazing, the twinkling is pretty. For precision astronomy, it's a disaster. They solved this with a revolutionary technology called adaptive optics. Here's how it works. You shine a powerful laser into the night sky, creating an artificial guide star. This artificial star is created by exciting sodium atoms in the upper atmosphere, about 90 kilometers up, causing them to glow. By tracking how the atmosphere distorts this artificial star, a known point source at a known location, you can calculate exactly how to deform your telescope's mirror in real time to cancel out the distortion. The result is dramatic. Without adaptive optics, images of the galactic center show a smeared blob. With adaptive optics, individual stars pop into sharp focus, each one trackable as it moves against the stellar background. The improvement in resolution is comparable to putting on glasses after years of blurry vision. Suddenly, the universe snaps into clarity. Both teams pushed this technology to its limits. They developed custom infrared cameras, optimized for the wavelengths that penetrate galactic dust. They built spectrographs that could measure the Doppler shifts of starlight, revealing how fast each star was moving toward or away from Earth. They refined their techniques year after year, observation after observation, slowly accumulating the data needed to map orbits that take years or decades to complete. Over the next 3 decades, both teams mapped the orbits of dozens of stars swirling around an invisible point. The star they watched most closely was called S2. S2 is a massive star, roughly 15 times the mass of our Sun, burning blue-hot and bright. It's a young star, astronomically speaking, only about 6 million years old, a cosmic infant compared to our 5 billion-year-old Sun, and it orbits the galactic center once every 16 years. That's an absurdly fast orbit for a star. For comparison, our Sun takes 230 million years to orbit the galactic center once. S2 completes its orbit in less time than it takes a human child to finish high school. And when S2 reaches its closest approach to the central object, it screams through space at more than 25 million kilometers per hour, nearly 3% of the speed of light. At that velocity, you could travel from Earth to the Moon in about 55 seconds. S2 passes within just 17 light hours of the central point, roughly 4 times the distance from the Sun to Neptune. By tracking S2's orbit with extraordinary precision, astronomers could measure what it was orbiting. The mass of the central object, calculated from the star's speed and orbital radius using Kepler's laws, came out to 4.3 million solar masses, and this mass was confined to a region smaller than our solar system, a volume with a radius of less than 17 light hours. Think about what that means. 4 million times the mass of the Sun, packed into a space smaller than the gap between the Sun and Neptune. The only thing in physics that can contain that much mass in that little space is a black hole. There was no other explanation, not a dense star cluster. The stellar velocities ruled that out. Not a cloud of exotic matter. It would emit radiation we'd detect. Not a ball of neutrinos or some other hypothetical structure. None of these could be stable at that density. The math pointed inexorably to a singularity hidden behind an event horizon, a supermassive black hole. In 2018, as S2 made its closest approach to Sagittarius A, both teams observed something remarkable. The light from S2 shifted toward redder wavelengths, not just because the star was moving away from us, but because the light was climbing out of an intense gravitational field. This is gravitational redshift, an effect predicted by Einstein's general relativity. Near a mass this extreme, time runs slower, and light loses energy escaping. The measurement matched Einstein's predictions exactly. In 2020, the team announced another remarkable finding. Over years of observation, they had watched S2's orbit shift. In Newtonian gravity, a planet or star traces the same ellipse over and over again, like a car on a racetrack. But in general relativity, orbits precess. They rotate slightly with each circuit, so the point of closest approach moves around the central object. This is called Schwarzschild precession, named after Karl Schwarzschild, the physicist who first solved Einstein's equations. The effect is tiny. For Mercury orbiting the Sun, it amounts to just 43 arcseconds per century. But it was this tiny discrepancy between Newtonian predictions and observed reality that first hinted that Newton's gravity was incomplete, and that helped confirm Einstein's general relativity in 1915. For S2 orbiting Sagittarius A, the precession is much larger, about 12 arc-minutes per orbit, roughly 1/5 of a degree. The team tracked this precession with exquisite precision, watching S2 trace out not an ellipse, but a rosette, a flower-shaped pattern where each orbital petal is slightly rotated from the last. This is one of the most precise tests of general relativity ever conducted in a strong gravitational field. And once again, Einstein was right. The observed precession matched the prediction exactly, within measurement uncertainty. As Reinhard Genzel put it, Einstein's general relativity predicts that bound orbits of one object around another are not closed, as in Newtonian gravity, but precess forward in the plane of motion. This famous effect, first seen in the orbit of the planet Mercury around the Sun, was the first evidence in favor of general relativity. 100 years later, we have now detected the same effect in the motion of a star orbiting the compact radio source Sagittarius A at the center of the Milky Way. 2 years later, in 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. Roger Penrose received the other half of the prize for his theoretical work on black holes. The evidence was overwhelming, but there was still something missing. We had proved the black hole existed through its gravitational effects. We had never actually seen it. In 2022, that changed. The Event Horizon Telescope is not a single telescope. It's a network of 8 radio observatories scattered across the planet in Hawaii, Arizona, California, Mexico, Chile, Spain, and Antarctica. By combining observations from all these facilities, astronomers created a virtual telescope the size of Earth. Here's the principle. Radio waves from a distant source arrive at different observatories at slightly different times, depending on the observatory's position. By recording these arrival times with atomic clock precision and combining the data afterward, astronomers can achieve the resolution of a telescope with a diameter equal to the maximum distance between observatories. In this case, roughly the diameter of Earth. This technique is called Very Long Baseline Interferometry, and it allowed the Event Horizon Telescope to achieve a resolution of 20 micro-arcseconds. That's like reading a newspaper in New York from a cafe in Paris, or spotting a donut on the surface of the moon. On multiple nights in April 2017, all 8 observatories pointed at the same target, the radio source, Sagittarius A high. They recorded a total of 5 petabytes of data, so much data that shipping hard drives by airplane was faster than transmitting it over the internet. The drives were sent to supercomputer correlators at MIT's Haystack Observatory and the Max Planck Institute for Radio Astronomy in Germany, where the data was combined and processed. The processing took 5 years. The reason Sagittarius A is a moving target, the black hole in the center of galaxy M87, which the Event Horizon Telescope had imaged 3 years earlier in 2019, is 55 million light-years away, but contains 6.5 billion solar masses. Material orbiting that black hole takes days or weeks to complete a circuit. Sagittarius A is much closer, only 26,000 light-years, but far smaller, with only 4 million solar masses. Material orbiting Sagittarius A completes an orbit in mere minutes. This means that during the hours-long observations, the appearance of Sagittarius A was constantly changing. Imagine trying to photograph a child while they're running and spinning. The Event Horizon Telescope team had to develop entirely new algorithms to account for this motion, averaging thousands of images to produce a single composite picture. And on May 12, 2022, they released it. The image shows a glowing ring, hot gas and plasma swirling around the event horizon at significant fractions of the speed of light, surrounding a dark central shadow. The ring appears brighter on one side due to Doppler effects. The gas moving toward us is brighter. The gas moving away is dimmer. This is not a photograph of the black hole itself. By definition, you cannot see a black hole. Light cannot escape from it. What you see is the boundary, the edge of the region from which nothing returns. The shadow in the center is the event horizon's silhouette against the surrounding inferno. This result provides overwhelming evidence that the object is indeed a black hole and yields valuable clues about the workings of such giants, which are thought to reside at the center of most galaxies. The Event Horizon Telescope collaboration announced in their official press release. The image was a long-anticipated look at the massive object that sits at the very center of our galaxy. Scientists had previously seen stars orbiting around something invisible, compact, and very massive at the center of the Milky Way. This strongly suggested that this object, known as Sagittarius A, is a black hole, and the image provides the first direct visual evidence of it. Sarah Issaoun, an astronomer at Harvard and co-lead of the project, described the result in the official announcement. "We were stunned by how well the size of the ring agreed with predictions from Einstein's theory of general relativity. The Event Horizon Telescope didn't just confirm the existence of Sagittarius A. It confirmed that general relativity works even in the most extreme gravitational environment in our galaxy. A theory written by a man in 1915, using only mathematics and thought experiments, sitting in a patent office in Switzerland and later a professor's study in Berlin, accurately predicts what happens at the edge of a 4 million solar mass black hole, 26,000 light years away. That is the power of physics. Let's pause here and consider what it took to get that image. The Event Horizon Telescope didn't just point cameras at the sky. It performed what might be the most coordinated observation in the history of astronomy. 8 facilities across 4 continents, each recording simultaneously, all requiring perfect weather, perfect timing, and perfect synchronization. The observations happened on 4 nights in April 2017. If a single facility had cloudy skies, the entire observation would be compromised. The baseline between observatories determines the resolution. Lose one telescope, and you lose the precision that makes the measurement possible. At each site, astronomers recorded incoming radio waves onto high-speed recorders developed at MIT's Haystack Observatory. These recorders captured data at a rate of 4 gigabytes per second. Over the course of the observations, the team accumulated 5 petabytes of data, about 5,000 terabytes. To put that in perspective, if you downloaded a movie from a streaming service every minute, it would take you 95 years to accumulate that much data. The data was too large to transmit over the internet. The hard drives had to be physically shipped to processing centers, flown on airplanes from Hawaii, from Chile, from the South Pole. The Antarctic data couldn't leave until the Southern Hemisphere winter ended and flights could resume. For months, priceless recordings of the Galactic Center sat in crates at the bottom of the world, waiting for summer. Once the data arrived at the correlators, supercomputers designed specifically for this task, the real work began. Each observatory had recorded the same radio waves, but at different times and from different positions. The correlators compared these recordings, calculating how the signals differed from one facility to another. These differences encode information about the source, the black hole's shadow, and the glowing ring around it. But there's a problem. The Earth's atmosphere distorts radio waves. Water vapor, turbulence, and temperature variations all affect the signals. The team had to model and correct for these distortions, essentially reverse engineering the atmosphere's effects to reveal the true signal beneath. And then there was the problem of Sagittarius A itself. The black hole is small enough, and the material orbiting it moves fast enough that the appearance changed significantly during the observations. The team couldn't just average the data. They had to develop new algorithms that could account for a moving, changing target. Chiquan Chan, an astrophysicist at the University of Arizona who worked on the imaging algorithms, explained the challenge. Making an image from EHT data is not easy. It's like trying to see the bottom of a river through rippling water while someone keeps stirring the river. The team generated thousands of images using different methods, different assumptions, different starting points. They looked for features that appeared consistently across all the methods, the things that couldn't be artifacts, that had to be real. They averaged thousands of images together, suppressing noise and reinforcing signal. The result, a blurry ring, about 50 microarcseconds across, with a dark center. It's not a photograph in the traditional sense. It's a reconstruction built from interferometry data, processed through sophisticated algorithms, validated against simulations of what a black hole should look like according to general relativity. And it matched. The predictions and the observations aligned. The size of the ring, the shape of the shadow, the brightness distribution, all consistent with Einstein's equations describing a 4 million solar mass black hole at a distance of 26,000 light-years. Ferial Ozel, an astrophysicist at the University of Arizona and a member of the Event Horizon Telescope team, put it this way at the 2022 press conference: "It seems that black holes like donuts." She was joking, but the observation is real. Both Sagittarius A and the black hole in M87 appear as bright rings around dark shadows. This is not a coincidence. It's physics. Now that we know what's there, we can ask the harder question: why is it there? The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across and containing somewhere between 100 billion and 400 billion stars. We live in a relatively quiet neighborhood in one of the spiral arms, about 26,000 light-years from the center. When you look up at the night sky and see the hazy band of the Milky Way stretching overhead, you're looking into the plane of our galaxy, toward and away from the dense central bulge. At the center of that bulge is Sagittarius A, and it's not alone. Nearly every large galaxy we've observed has a supermassive black hole at its center, some far larger than ours. The black hole in M87, the first ever imaged by the Event Horizon Telescope, contains 6.5 billion solar masses. Some supermassive black holes weigh tens of billions of solar masses. The current record holder, TON 618, may contain 66 billion solar masses, a single object containing more matter than our entire galaxy. This ubiquity raises a profound question. Which came first, the galaxy or the black hole? For a long time, astronomers assumed galaxies formed first, and supermassive black holes grew within them later, fed by gas falling toward the galactic center. But observations from the James Webb Space Telescope have complicated this picture. We've found supermassive black holes in the very early universe, existing when the cosmos was less than 1 billion years old. Some of these black holes are too massive to have grown from stellar mass seeds in the time available. This suggests that supermassive black holes might seed galaxy formation, not the other way around. The black hole comes first, and the galaxy coalesces around it. Or perhaps both form together, co-emerging from the same primordial conditions. The relationship is still being unraveled. The relationship between supermassive black holes and their host galaxies is one of the strangest in astrophysics. There's a tight correlation between the mass of a supermassive black hole and the mass of the galactic bulge surrounding it. This isn't a coincidence. It suggests that galaxies and their central black holes grow together, co-evolving over billions of years. But how does a supermassive black hole form in the first place? Ordinary stellar black holes form when massive stars die. A star more than about 20 times the mass of the Sun will, at the end of its life, collapse under its own gravity, leaving behind a black hole with a mass of perhaps 10 to 50 solar masses. But there's a problem. To grow from tens of solar masses to millions or billions of solar masses through ordinary accretion, matter falling in, would take longer than the age of the universe. Yet we observe supermassive black holes in galaxies that existed when the universe was less than 1 billion years old. These black holes somehow reached billions of solar masses in a cosmic eye blink. There are several theories. Perhaps the first black holes were born directly from collapsing gas clouds in the early universe, skipping the star phase entirely and forming seed black holes of thousands or millions of solar masses. Perhaps the earliest black holes grew at rates that defy our current understanding of physics. Perhaps primordial black holes formed in the density fluctuations of the Big Bang itself. We don't know. This is one of the great unsolved problems in astrophysics. What we do know is that supermassive black holes and their host galaxies are intimately connected. There's a tight relationship between the mass of a supermassive black hole and the velocity dispersion of stars in the surrounding galactic bulge. The faster the stars move, the more massive the black hole. This relationship holds across galaxies of wildly different sizes and types, suggesting that black holes and galaxies grow together in some kind of cosmic feedback loop. One possibility: as a supermassive black hole actively feeds, it releases tremendous energy. Jets of plasma driven by magnetic fields near the event horizon can punch out of the galaxy entirely, heating surrounding gas and preventing it from cooling and forming new stars. This AGN feedback regulates star formation, linking the black hole's appetite to the galaxy's growth. Another possibility: the same processes that funnel gas into the galactic center to form stars also funnel gas into the black hole. Galaxy mergers, for instance, can drive enormous quantities of gas toward the center, simultaneously triggering bursts of star formation and episodes of black hole growth. The relationship between Sagittarius A and the Milky Way is one example of this cosmic partnership. The black hole didn't just happen to form at the center of our galaxy. It grew with the galaxy, shaped by the same processes that built the spiral arms and the bulge and the halo of dark matter that holds everything together. What we do know is that Sagittarius A is relatively calm as supermassive black holes go. Many galaxies have active galactic nuclei, central black holes that are actively feeding, consuming enormous quantities of gas and releasing tremendous amounts of energy in the process. Some release jets of plasma traveling at nearly the speed of light, visible across millions of light years. The quasars observed in distant galaxies are powered by supermassive black holes accreting matter so vigorously that they outshine their entire host galaxies by factors of hundreds. Sagittarius A isn't doing that. It's quiet. It's not actively feeding on large quantities of gas. The luminosity of our galactic center is billions of times lower than it could be if Sagittarius A were eating its fill. Why is our black hole so quiet? There simply isn't much gas falling into it right now. The galactic center is relatively cleared out, swept clean by past activity. But this won't last forever. In about 4 billion years, our galaxy will collide with Andromeda, our nearest large neighbor. When galaxies collide, they don't smash into each other like billiard balls. The stars are too spread out for that. Instead, the galaxies pass through each other, gravitationally disrupting their structures. Gas clouds collide and compress. Star formation ignites in bursts, and vast quantities of gas are funneled toward the merged galactic center. When that happens, Sagittarius A will wake up. Gas will spiral inward, forming an accretion disk around the event horizon. Friction within the disk will heat the gas to millions of degrees. The black hole will begin to glow with the radiation of infalling matter, possibly launching jets of plasma that will be visible across the merged galaxy. For a time, millions of years, perhaps, Sagittarius A will become an active galactic nucleus, outshining billions of stars. This isn't speculation. We see active galactic nuclei throughout the universe, the brilliant quasars that outshine their host galaxies, the ciphered galaxies with their glowing cores, the radio galaxies with their enormous jets. These are the feeding black holes, the active monsters. Our black hole is simply taking a nap. In 2024, the Event Horizon Telescope released a new image of Sagittarius A, this time in polarized light. This image revealed something unexpected: organized spiraling magnetic fields near the event horizon, strikingly similar to those observed around the much larger black hole in M87. This similarity suggests that strong magnetic fields may be a universal feature of supermassive black holes. It also hints at something fascinating. Sagittarius A may have a jet, a stream of plasma being launched from near the event horizon. We haven't detected it yet, but the magnetic field structure suggests it could be there, hidden from our current instruments. The black hole at the center of our galaxy is a sleeping giant. It's been quiet for millions of years, but it won't be quiet forever. To truly appreciate what a black hole is, you need to understand what happens when something falls into one. And here is where the physics gets genuinely strange. Imagine you're an astronaut approaching Sagittarius A. At first, nothing seems unusual. Space around you appears normal. The stars shine. Your instruments read nominal. You feel weightless, as you would anywhere in free fall. But as you get closer, the gravitational field intensifies, and it doesn't intensify uniformly. The gravity at your feet, if you're falling feet first, is slightly stronger than the gravity at your head, because your feet are slightly closer to the black hole. This difference in gravitational force across your body is called a tidal force. You experience tidal forces right now on Earth. The moon's gravity pulls slightly harder on the side of Earth facing it than on the far side, which is why we have ocean tides. But near a black hole, these tidal forces become extreme. Your body is stretched in the direction of the black hole and compressed from the sides. You're pulled like taffy. Physicists have a term for this process: spaghettification. The word is almost comical, but the process is not. Stephen Hawking popularized the term in his book, A Brief History of Time, describing a fictional astronaut's unfortunate encounter with a black hole. As you approach the event horizon, you're stretched into a thin strand, a human noodle, and eventually torn apart at the atomic level. For stellar mass black holes, the kind that form from dying stars, spaghettification happens well outside the event horizon. The gravity gradient is steep, and you'd be shredded long before you reach the point of no return. For supermassive black holes, like Sagittarius A, the situation is different. The event horizon is much larger, and the tidal forces are gentler at that boundary because the black hole is so spread out. An astronaut might cross the event horizon of Sagittarius A intact, noticing nothing unusual at the moment of crossing. There's no barrier, no sign, no physical sensation marking the boundary. But their fate is still sealed. Once you cross the event horizon, your future contains only one destination: the singularity. This is not about speed or trajectory. Inside the event horizon, the singularity is not a place in space. It's a moment in time. All possible paths lead there, just as all moments in normal spacetime lead to the future. You cannot avoid the singularity any more than you can avoid tomorrow. This is perhaps the strangest aspect of a black hole's interior. Outside the event horizon, space and time behave the way we intuitively expect. You can move freely in any spatial direction. Time flows forward regardless of your motion. Inside the event horizon, the roles of space and time effectively swap. The radial direction, toward or away from the singularity, becomes time-like. Moving toward the singularity is no longer a spatial journey. It's the inevitable passage of time. Think about it this way. You cannot travel backward in time. Once a second has passed, it's gone. Inside a black hole, the singularity is your future in precisely that sense. Every moment that passes brings you closer to it. Trying to escape by accelerating outward is like trying to travel to yesterday, physically meaningless. And at the singularity, according to general relativity, space-time curvature becomes infinite. Density becomes infinite. Volume becomes zero. The laws of physics, as we understand them, cease to apply. We don't know what actually happens there. General relativity predicts a mathematical infinity, a sign that the theory is breaking down, that something else must take over, that something else is presumably quantum gravity, a theory that unites quantum mechanics with general relativity. We don't have such a theory yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none is complete. The singularity inside a black hole is one of the places where our ignorance is most profound. Some physicists speculate that the singularity isn't truly a point of infinite density, but something more complex, perhaps a region where quantum effects prevent further collapse, perhaps a gateway to another region of space-time, perhaps something we can't yet imagine. The firewall paradox and related debates suggest that even the event horizon might behave differently than classical relativity predicts when quantum effects are fully accounted for. These are not just abstract puzzles. Understanding what happens inside black holes may be essential to understanding the origin of the universe itself. The Big Bang, in standard cosmology, emerged from a singularity, a point of infinite density and temperature from which all of space and time expanded. If we can understand the singularities inside black holes, we may gain insight into the singularity from which everything we see originated. Sagittarius A, sitting at the center of our galaxy, contains a singularity. Somewhere within its event horizon, space-time is doing something that our best theories cannot describe, and we've photographed the boundary that hides it. Now, here's where it gets stranger still. As you fall toward a black hole, something remarkable happens to time. From your perspective, nothing unusual occurs. You fall faster and faster. Your clock ticks normally, 1 second per second, as always. You might watch a movie on your tablet, and it would play at normal speed. You might check your pulse, and it would beat at its normal rate. The laws of physics, locally, appear completely ordinary. You cross the event horizon without ceremony. There's no physical barrier, no warning sign, no alarm, and continue falling toward the singularity. From the moment you cross the horizon to the moment you reach the singularity, perhaps a few seconds pass by your clock for a black hole of Sagittarius A's size. But from the perspective of an observer far from the black hole, watching you fall, something entirely different happens. As you approach the event horizon, your time appears to slow down. Your movements become sluggish. If you were waving goodbye, your hand would seem to move slower and slower. Light from you becomes red-shifted, stretched to longer wavelengths, as it fights to escape the intensifying gravity. You appear dimmer and dimmer, redder and redder. You appear to freeze at the edge of the event horizon, never quite crossing it, fading into invisibility over an eternity. An outside observer, watching with perfect instruments, would never see you cross the event horizon. You would simply fade, asymptotically approaching the boundary, redshifting beyond visibility, until you were indistinguishable from the black hole itself. Both perspectives are valid. Both are real. There's no contradiction, just different views of the same physics from different reference frames. This is gravitational time dilation, and it's not a trick or an illusion. Near a mass as extreme as Sagittarius A, time genuinely runs slower. The Event Horizon Telescope's image captures this effect frozen in light. The glowing ring around Sagittarius A Ghez is hot gas orbiting at tremendous speeds. Its light gravitationally lensed and time dilated by the black hole's gravity. The dark shadow in the center is the region where light cannot escape, where time, from our distant perspective, effectively stops. But there's more to the image than just a ring around darkness. The extreme gravity of the black hole bends light from behind it, creating a phenomenon called gravitational lensing. Light that passed close to the event horizon, but not close enough to fall in, was curved around the black hole, reaching our telescopes from angles that would be impossible in flat space-time. This means the ring we see isn't just light from gas in front of the black hole. It includes light from gas behind the black hole, bent around and delivered to us by the curvature of space-time. The black hole acts as a cosmic lens, distorting the light of everything around it into that characteristic ring shape. Einstein predicted gravitational lensing in 1936, though he doubted it would ever be observed. He was wrong again. Today, gravitational lensing is a major tool in astronomy, used to detect dark matter, measure the expansion of the universe, and find exoplanets. And the most extreme gravitational lensing in our galaxy occurs around Sagittarius A, sculpting light into the glowing ring that the Event Horizon Telescope captured. In 1974, physicist Stephen Hawking made a startling prediction. Black holes, he argued, are not completely black. This sounds contradictory. By definition, nothing escapes from within the event horizon. But Hawking's insight came from the intersection of quantum mechanics and general relativity, two theories that don't play nicely together and whose conflict lies at the heart of modern theoretical physics. Quantum mechanics tells us that empty space isn't truly empty. The vacuum seethes with quantum fluctuations, virtual particles constantly popping into existence and annihilating each other so quickly that they don't violate the conservation of energy. This happens everywhere, all the time, and normally has no macroscopic effect. But near the event horizon of a black hole, something strange occurs. The intense gravitational field changes the rules. Hawking showed that the curvature of space-time near the horizon causes these vacuum fluctuations to produce real particles. Energy is extracted from the gravitational field itself, and particles are created and emitted. The popular explanation involves virtual particle-antiparticle pairs, with one falling in and one escaping. This picture, which Hawking himself used in his book A Brief History of Time, is an oversimplification. The real mechanism involves the quantum properties of fields in curved spacetime. But the result is the same. Black holes emit radiation. This radiation is incredibly faint. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. Smaller black holes are hotter. For Sagittarius A, with its 4 million solar masses, the Hawking temperature is about 10^14 Kelvin. That's about 100 trillion times colder than the coldest temperature ever achieved in a laboratory. It's so cold that the cosmic microwave background, the 2.7 Kelvin afterglow of the Big Bang, overwhelms it completely. But the radiation exists, and over time, immense, incomprehensible time, it causes black holes to shrink and eventually evaporate. As energy is radiated away, the black hole loses mass. As it loses mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates more intensely. This feedback loop accelerates the evaporation. Slowly at first, faster and faster, until the black hole reaches a final, catastrophic burst. The evaporation time depends enormously on the black hole's mass. A black hole with the mass of a mountain would evaporate in about 1/1000th of a second, exploding with the energy of a thermonuclear bomb. A black hole with the mass of the Earth would take about 10⁻50 years to evaporate, vastly longer than the current age of the universe. For Sagittarius A, with its 4 million solar masses, the evaporation time exceeds 10^87 years, a number so large it dwarfs the current age of the universe by a factor beyond comprehension. The cosmic microwave background, the afterglow of the Big Bang, has a temperature of about 2.7 Kelvin. Sagittarius A has a Hawking temperature of about 10^14 Kelvin, far colder than the background radiation. This means Sagittarius A currently absorbs more radiation from the universe than it emits. It's growing, not shrinking. But in the far, far future, when the universe has expanded and cooled enough that even the cosmic microwave background has faded below the temperature of Hawking radiation, the black holes will begin to dominate. They will be the last engines of entropy, the final thermodynamic machines, slowly evaporating over timescales we cannot truly imagine. And when they're gone, nothing will remain but a thin mist of radiation and elementary particles, diffusing forever into an infinitely empty, dark, cold universe. This is the ultimate fate of Sagittarius A, not destruction by collision or consumption, but a slow fade into nothingness over timescales that make the current age of the universe look like the first instant of a cosmic heartbeat, Hawking radiation introduces another puzzle, perhaps the deepest in theoretical physics, the black hole information paradox. In quantum mechanics, information is conserved. The laws of physics are reversible. If you know the complete quantum state of a system, you can calculate both its future and its past. Information cannot be created or destroyed. But if a black hole evaporates through Hawking radiation, what happens to the information about everything that fell in? Hawking's original calculations suggested the radiation is perfectly thermal, random, carrying no information about the black hole's contents. This would mean that when the black hole finally evaporates, all information about what went into it would be permanently lost. This contradicts quantum mechanics at its core. For decades, physicists have wrestled with this paradox. Some proposed that information somehow escapes encoded in subtle correlations in the Hawking radiation. Others suggested that black holes leave behind remnants containing the missing information. Still others proposed modifications to quantum mechanics itself. Recent theoretical work, including calculations involving the page curve and insights from string theory and the ADS-CFT correspondence, suggests that information is indeed preserved, that Hawking radiation is not perfectly random, but carries subtle imprints of everything that fell into the black hole. The information escapes, scrambled almost beyond recognition, but not truly destroyed. We don't yet have a complete understanding. The resolution of the black hole information paradox likely requires a theory of quantum gravity, the same theory needed to understand what happens at the singularity. These questions are connected. The interior of a black hole and the nature of its evaporation are linked puzzles, and solving one may solve the other. Some physicists believe the solution lies in holography, the idea that all the information about a black hole's interior is encoded on its surface, like a cosmic hologram. This would mean the interior of a black hole isn't really a separate region of space, but is somehow equivalent to information stored at the event horizon. The mathematics supporting this view is compelling, but the physical interpretation remains debated. Others propose that black holes never truly evaporate completely, but leave behind remnants, tiny, extremely dense objects containing all the information that fell in. Still others suggest that space-time itself behaves differently than classical physics predicts, with quantum effects creating subtle correlations in the Hawking radiation that preserve information in ways we're only beginning to understand. What's remarkable is that a 4 million solar mass black hole, 26,000 light-years away, is forcing us to confront these fundamental questions. Sagittarius A isn't just an astrophysical object, it's a laboratory for testing the deepest ideas in physics. The image released in 2022 confirms general relativity. But the full understanding of what that image represents, what's really happening at the event horizon and beyond, requires physics we haven't yet discovered. Let's step back and appreciate where we are. You are sitting on a planet orbiting a medium-sized star in the disk of a spiral galaxy. That galaxy contains hundreds of billions of stars, all orbiting a common center 26,000 light-years away. At that center is a point of infinite density, an object containing 4 million solar masses, surrounded by an event horizon from which nothing can escape. We've known about black holes theoretically for over a century. We've had strong circumstantial evidence for Sagittarius A for 3 decades. But in 2022, We photographed it. The image is blurry by everyday standards, a smeared ring of orange light. But consider what it represents. Light that was emitted millions of years ago from gas heated to billions of degrees, orbiting at a significant fraction of the speed of light, around an object so massive it warps space-time itself, captured by a virtual telescope spanning the entire Earth, processed by supercomputers, running algorithms derived from Einstein's equations. This is what humanity can do. We can look at the center of the galaxy and photograph the boundary of a black hole. And here's the thing about Sagittarius A that I find most profound. It has no idea we're watching. It's a gravitational engine, mindlessly processing matter and energy according to the laws of physics. It doesn't know that a species of bipedal primates on a small rocky planet 26,000 light-years away has spent a century figuring out what it is, tracking the stars that orbit it, developing the technology to photograph it, and arguing about what happens to information that falls past its event horizon. The black hole at the center of the Milky Way is exactly what the mathematics predicted it would be. It obeys Einstein's equations. It behaves as Penrose proved it must. It exists without regard to our comprehension. But we comprehend it anyway. We've dragged understanding from the cosmos through sheer determination, ingenuity, and the accumulated effort of thousands of scientists across generations. The story isn't over. The Event Horizon Telescope is expanding. New observatories are being added to the network, facilities in Greenland, in the French Alps, in Africa. Each new telescope adds baselines, improving resolution and filling gaps in coverage. Future observations will capture not just still images, but movies, actual footage of material swirling around black holes, changing in real time. The next generation Event Horizon Telescope, the NGGEHT, will double the number of dishes in the global array. It will observe at new frequencies with better resolution. Michael Johnson, an astrophysicist at Harvard and a member of the NGEHT planning team, describes the goal. We want to make black hole movies. We want to watch gas spiral in, see magnetic field lines twist and snap, observe the chaotic dynamics near the event horizon in real time. This isn't science fiction. The technology is being developed now. Within a decade, we may watch Sagittarius A act devour a cloud of gas, seeing the material glow as it accelerates toward oblivion. Beyond that, future megascopes, like the European Extremely Large Telescope, may find stars orbiting even closer to Sagittarius A than S2. These stars could let us measure the black hole's spin, its angular momentum, revealing how it formed and grew over billions of years. Black holes, you see, can spin. When they form from rotating stars, or when they grow by swallowing matter with angular momentum, they acquire rotation. This spin affects the space-time around them, dragging it into a vortex, an effect called frame dragging, or the lens-thirring effect. Near a spinning black hole, even light must rotate with the vortex. We don't yet know how fast Sagittarius A is spinning. The current observations don't have enough precision, but stars orbiting closer than S2, if we can find them and track them, might show us. If we're lucky, we might find stars so close that frame-dragging effects become measurable, letting us probe not just the mass of the black hole, but its angular momentum, its history, its formation. These observations could test general relativity in regimes we've never accessed before. They could reveal new physics. They could tell us whether the no-hair theorem is correct, whether black holes really are characterized only by mass charge, and spin, or whether they hide additional structure. The no-hair theorem, proposed by John Wheeler, states that a black hole can be completely described by just 3 numbers: its mass, its electric charge, and its angular momentum. All other information about what fell in, the chemistry, the structure, the history, is lost. The black hole has no hair, no distinguishing features beyond those 3 properties. A black hole made of compressed hydrogen would be identical to a black hole made of compressed lead, as long as the mass, charge, and spin matched. This is a remarkable claim, and testing it is a major goal of future observations. If we can measure the space-time around Sagittarius A head precisely enough, we can check whether it matches the predictions of a Kerr black hole, the solution to Einstein's equations describing a rotating black hole, or whether there are deviations that would hint at new physics. Some theorists propose that quantum effects might give black holes hair after all, subtle features that violate the classical theorem. Others suggest that deviations from the Kerr solution might reveal the presence of exotic matter or modified gravity. Sagittarius A, as the closest supermassive black hole to Earth, is our best laboratory for these tests. And beyond Sagittarius A, there are billions of other supermassive black holes in billions of other galaxies. Some are actively feeding, powering quasars visible across the universe. Some are quiet, like ours. Understanding the full population of supermassive black holes, how they form, how they grow, how they influence galaxy evolution, is one of the great projects of 21st century astronomy. Every major galaxy has one of these monsters at its heart. The Andromeda Galaxy, our nearest large neighbor, has a black hole of about 100 million solar masses, 25 times more massive than Sagittarius A. The giant elliptical galaxy M87 hosts a 6.5 billion solar mass beast, the first black hole ever photographed. And in the cores of distant quasars, black holes of tens of billions of solar masses pour out more energy than all the stars in their host galaxies combined. These objects shape the universe on the largest scales. The jets they launch can extend millions of light years, influencing the formation of galaxies and the distribution of matter across cosmic voids. The radiation they emit when feeding can heat gas across entire galaxy clusters, preventing it from cooling and forming stars. Supermassive black holes are not just curiosities, they're cosmic architects. And we have one right here at the center of our own galaxy. Quiet now, but eternally patient, waiting for the next meal, anchoring the rotation of hundreds of billions of stars, including the one that warms our world each morning. So what is at the center of the Milky Way? A black hole, a supermassive one, 4 million times the mass of the Sun, confined within an event horizon roughly 23 million kilometers across, less than the distance from the Sun to Mercury. It's called Sagittarius A, and it has been sitting there for billions of years, growing slowly by consuming gas and stars, influencing the orbits of everything around it, invisible except for the gravitational fingerprints it leaves on space-time. We found it by accident in 1933, when a radio engineer building antennas for telephones detected signals from the galactic center. We confirmed it over 3 decades of painstaking observation, watching stars whip around an invisible point at millions of kilometers per hour. We photographed it in 2022 using a telescope the size of Earth, and the image matched Einstein's predictions from 1915 with stunning precision. The black hole at the center of our galaxy is proof that the universe is stranger than we ever imagined, and that our ability to understand it is greater than we ever dared hope. It's a monster, but it's our monster. It sits at the heart of our home, the anchor around which our entire galactic neighborhood revolves. We live in the suburbs of a galaxy organized around a 4 million solar mass singularity. And somehow, against all odds, we figured that out. Consider the chain of reasoning that led us here. Einstein, working in a patent office in Bern, imagined what it would be like to ride on a beam of light, and from that thought experiment derived the relationship between space and time. Schwarzschild, crouching in a trench on the Eastern Front, solved Einstein's equations and found a point of infinite density. Jansky, troubleshooting phone static in New Jersey, detected radio waves from the center of the galaxy. Penrose, walking through London, conceived of trapped surfaces and proved that singularities must form. Genzel and Ghez, competing from opposite sides of the world, tracked stars for 30 years to prove that something massive and dark lurked at the galactic center. And hundreds of scientists from 80 institutions coordinating observations across the entire planet synthesized an image of what Jansky's static had been telling us all along. This is what science does. It takes the raw data of the universe, light, radio waves, the motion of distant objects, and extracts understanding. Not opinion, not belief, but demonstrable, testable, reproducible understanding. The next time you look up at the night sky and see the hazy band of the Milky Way, remember what's hiding there, 26,000 light years away, in the direction of Sagittarius, a place where space curves so severely that light cannot escape, a boundary between our universe and something we cannot directly observe, a laboratory where the most extreme physics in our galaxy plays out continuously, silently, indifferent to whether we're watching. And yet, despite that indifference, the universe has handed us the tools to understand it. The laws of physics, written in mathematics, apply everywhere, from the laboratory bench to the edge of a black hole. The same equations that describe light bending through a glass lens describe light spiraling around a 4 million solar mass singularity. The same principles that govern your heartbeat govern the orbital mechanics of stars dancing around the galactic center. This is the deepest mystery and the greatest gift of science, that the universe is comprehensible. Not fully. We have enormous gaps in our understanding, paradoxes we cannot resolve, phenomena we cannot explain. But partially, incrementally, astonishingly, we can figure things out. We can look at a smeared ring of light from the other side of the galaxy and say, with confidence, that's a black hole. And here's how we know. We are watching now, and we finally know what we're looking at.